Hello. In this presentation, I will outline a vertical machine learning platform and draw comparisons to EDA tools. The Looper platform, developed in my group at Meta, makes it easy to embed machine learning into software systems. It is used via an API for collecting training data and for making decisions or predictions. The machine learning code stays separate from the application code. Example applications include data-driven personalization and adaptive interfaces, prefetching to reduce latency, content ranking, and so on. The platform supports supervised and reinforcement learning, classification and regression, and also a variety of model types such as deep learning and XGBoost. It is used by over 90 product teams at Meta, deploys over 400 machine learning models at once, and makes 4 to 6 million decisions and predictions per second. The figure compares horizontal ML platforms, which are essentially toolboxes such as PyTorch, to vertical ML platforms that support the entire ML design cycle from problem type selection to product impact evaluation and optimization. A significant amount of automation is used to optimize the models, simplify maintenance, and ensure product impact. The two columns in the figure compare specialized to general-purpose platforms. General-purpose platforms use more automation to support a wider variety of use cases. Now, to illustrate EDA design flows, I refer to the physical design textbook I co-authored with Andrew Kang, Jens Lienig, and Jin Hu. If you look at the cover carefully, you will see a design flow. Let's zoom into this design flow. The chip planning stage defines design blocks and is hard to automate because it optimizes several objectives based on incomplete information. Later on, the global placement step is sometimes confused with chip planning because it can deal with large macros. But here, many small standard cells are placed as well, which diminishes estimation uncertainty. Mixed size placement has been successfully automated in modern tool chains at a very large scale. We are now comparing two domains. In the Looper platform, AI outputs are predictions or decisions, but EDA flows solve synthesis and optimization tasks. In Looper, a lot of data is available on the same platform, and it is used for training ML models. When dealing with EDA flows, the number of chip designs is small, and no one sees a large fraction of them because they are proprietary. Because of this, established EDA techniques are not ML-based and instead optimize mathematical objectives. However, the two domains have many things in common. During end-to-end optimization, product impact cannot be captured in closed form. In online systems, user engagement metrics are measured on live data, and in EDA, full chip performance is estimated algorithmically. The good news is that simple objectives approximate product metrics quite well. If some ML models lose by over 10% in simple metrics, they're likely useless. Likewise, if some placer loses by over 10% in half perimeter Y-length, it likely loses in other metrics. Researchers are often tempted to claim otherwise, but this is really a trap. In practice, it is common to optimize simple objectives first, then tune for product impact. A natural and very general idea is to optimize hard-to-capture product objectives using reinforcement learning. We implemented this idea successfully at Meta. We found that reinforcement learning is inherently difficult to use. It needs a lot of training data, is slow and fragile, and often exhibits poor out-of-distribution performance if you are not careful. Even when it works, as in our case, it works in production, more conventional, robust baselines get close and in many cases do better. Another thing in common between machine learning and EDA is the belief in magic. The science fiction quote given here tells us that any sufficiently advanced technology is indistinguishable from magic. But even in actual research, we have seen striking breakthroughs: simulated annealing, deep learning, reinforcement learning for games. However, there have also been many false starts and benchmarking mistakes. For example, Patrick Madden wrote a paper describing such examples for placement. To ensure that progress is real, very important are the culture of public benchmarking, contests, and reproducibility of results. This is equally true in the ML community and in the EDA community. In particular, impactful advances in placement have been validated by contest wins. This panel was partly motivated by recent work that applied deep reinforcement learning to mixed-size placement. The idea was to adapt reinforcement learning breakthroughs to outdo mathematical optimization in mixed-size placement. The main results reported were on selected proprietary circuits with a full commercial design flow. To me personally, the paper leaves serious doubts about empirical results and top-line claims. Contrary to claims of fast chip design, reinforcement learning appears slow, much slower than competing analytical placers. In the author's open source code, RL is post-processed by simulated annealing and coordinate descent, but there are no ablation studies, and this post-processing is not applied with competing methods in experiments. The open source version is missing an important piece, pre-processing, and it does not run on typical circuits. This is 10 months after the publication of the Nature paper. The quote in the red frame is from the GitHub from the authors. Reinforcement learning in that paper is compared only to other methods after pre-processing, and this pre-processing represents a 20-year-old approach. Modern mixed-size placers do not need such clustering and promise stronger results. This is a major design flow concern about the methodology in that paper. But what I find particularly striking is that 10 months after the publication, the authors have not produced compelling results on common mixed-size benchmarks. I hear that physical design experts ask the authors for benchmark results for some time. As you see, machine learning platforms and EDA flows have a lot in common, both in how components are assembled into larger systems and in how scientific results should be evaluated.